Recall that our model for exponential growth is going to be this. A times 1 plus r raised to the t. A represents my initial amount, how much I start with. The 1 is in there because we're always starting at 100% and then either adding or subtracting depending on if we have an increase or decrease problem. R represents our growth rate or our decrease rate as a decimal always, and then t represents time. So let's go ahead and take a look at this example and get some numbers plugged in there into our model. And go from there. So we're starting with a zombie infestation, always a good way to represent exponential growth. And it says the zombie infestation began with a single zombie. So there's some important information that tells me my initial value, the A, is going to be 1 in this case. And then doubled each day. Well, doubling means a 100% increase. So my R is 100%, but remember that always has to be expressed as a decimal. So divide that number by 100 to get the decimal, so that's actually going to be just 1 when I divide that by 100, or move your decimal over 2 spaces. Growing exponentially, blah, blah, blah. How many zombies were there after 5 days? So there's the time that I'm dealing with first. Okay, so let's go ahead and get all that plugged into this model and see what happens. So our A value, our initial amount, is 1. In parentheses, I have 1. That 1's always there, plus the rate, which is 1. So there's lots of 1's in this example. Make sure you know which one is which, I suppose. And then I'm raising that to the 5th power to represent the 5 days. Okay? If I want to do a little bit of simplifying, even though it's not necessary, because I'm just going to type this in my calculator, I can write this as 1 times 2 to the 5th power. Now for all these problems, I would recommend you just type them in your calculator just as they appear. If you are doing them piece by piece, remember, exponents come before you multiply, so make sure you do 2 to the 5th first, and then multiply by 1, or whatever your numbers happen to be, but make sure you do the exponent first, or just follow my advice and just type the whole thing in at once. Once I do this, I realize that after 5 days, there's going to be 32 zombies. Not many, but remember, exponential growth starts out really slow and then continues to increase very quickly as time goes on. For the next part of this problem, they asked me about 15 days or 25 days. Well, all that's going to be changing then in my model is just going to be my exponent. Everything else is going to remain the same. So what I'd like you to do is pause the video and try to work those two out. Make sure you're getting the answers that I'm getting. So here are my two models and my two answers. Notice all I did was change the exponent. Everything else remained the same. So 15 days ended up with about 32,000 zombies. And after 25 days, I'm over 33 million zombies. So once again, we see that idea of exponential growth starting out really slow, but then continuing to increase very, very quickly as time goes on. Okay, take a look at this next part of the problem. In this case, I want to know how many days is it going to take until the zombies pretty much have wiped out everybody on Earth. So I'm using a population of about 7 billion people as our Earth's population today. So notice this question is a little bit different than what's above, because this time I don't know the time. So let's kind of start to write this out and see if we can come up with some ideas on how to solve this. So the number 7 billion has 9 zeros in it, so let's make sure I get all those down. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's what I want the answer to be. This time I'm going to set that equal to 1 times 2 to the, well, I don't really have any idea what that exponent's going to be, so I'm just going to put it to the x power. Now, we have a brand new kind of equation to solve. I don't know how to get an x out of an exponent. Or if you're watching this as a review video, at that point, maybe you do. Maybe you know about logarithms. But at this point in our lesson, we don't know how to get that x out of there. So instead, I really only have two options. I asked you guys in class what we could try, and many of you said, well, why don't you just guess and check, which at this point I think is a fantastic idea. It's one of the few options we have. So start plugging in some different values for x and see what's going to get you an answer of 7 billion. Now, we probably won't get 7 billion exactly. So all I would want would be a range, like between day 40 and day 41, or between day 55 and 56. I would just want the range of values from when we go under 7 billion to over 7 billion. So that would be one method. The other method that some people came up with was that we could graph it. And I thought that was an excellent idea. It's a way that we can get a much more accurate answer than just guess and check. If we were going to graph it, I'd say, and remember we've talked about this idea before too, I would enter one side of my equation as y1 and enter the other side of the equation as y2. So tell you what, let's switch over to the calculator and take a look at each of those methods, the guess and check method and the graphing method, and see what answer we come up with. So we've just figured out there are two ways we can go about answering the second part of this question. One method is to guess and check. And so here's the problem that we were working with. 7 billion is what we want to figure out as our population, and the model we're using is just 2 to the x, or 1 times 2 to the x. So it's as simple as, yeah, using guess and check. I know from our previous part of the problem that after 25 days there were 33 million zombies, so I know my answer has to be bigger than 25 and probably not much bigger. So maybe we try graphing, or try calculating 2 to the 30th power, 30 days. I hit enter and I can count that out and see that I'm just over a billion, so let's try maybe a little bit higher. One trick, if you don't want to retype the thing in every time, is just press enter, or press up, and then press enter. You can reselect what you typed in and just type over it. So maybe I want to try 32 days. And I can see that I'm getting close. I'm at 4 billion. So let's try this again. So go back up there, press enter to pull that back down. Maybe try 33 days and see where we're at that point. And so I can see, okay, all of a sudden I'm over 7 billion. So I'm going to say for my answer, as specific as I can be right now, is that between 32 and 33 days, that's where it changes, where it goes from under 7 billion to over 7 billion. Now, if you want to be more specific, which you don't have to be for me, that's okay for right now, you could try doing 32.5 or 32.4, and you can try to get it that way. Or we could try the second method, which was to graph. So let's take a look at how that works. Remember, we've talked previously about how to solve almost any problem in algebra by graphing. And so go into your graph, and I've started by typing in the two sides of my equation. So as y1, I typed in 7 billion. Make sure you have enough zeros in there. There should be 9 zeros. And then as y2, type in your equation, 1 or just 2 to the x, or 1 times 2 to the x. Be careful that you type an x in there. If you just type a number for x, it's going to graph a line, because 2 to some number is just, a number. I want to make sure that's changing. So I want to find where these two graphs intersect. I'm going to, of course, have to change my window from the 10 by 10 window. So x stands for the number of days, so it makes sense to go 0 to, well, I kind of already know the answer, so I'm just going to, pretend I didn't know and say, well, maybe 35 days. And I don't really know that number. I'd have to, make it bigger or smaller depending if I don't see that intersection point, but I kind of know that's going to work this time. For your y, your output, I know how high this graph needs to go. Since it represents a population, I'm going to start from 0 because I can't have negative population, and it needs to go up at least as high as 7 billion, so let's just go up to 10 billion. So I've got the 10 in there, so let's add 9 zeros after that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And I think I got enough in there. Let's hit graph and see if we can see our intersection point. So there's where the population is 7 billion. There is the zombie population. Notice it's very, very low for a long time, and then it starts to skyrocket over time. So yes, I can see that intersection right there. If I couldn't see it, I'd have to adjust my window. Let's hit second trace, remember, to find the intersect button. So then option 5. And I want to just trace over close to it, or since there's only one intersection point, I should be able to just from here press enter 3 times. So 1, 2, 3, and there it is. Like we said, between day 32 and 33 is when it happens, and specifically we're coming up with about 32.7 days until humanity is doomed.